Hello students, in this video we are going to discuss about valence bond model for intrinsic semiconductor. As we have studied about the classification of semiconductor, there are two types, intrinsic and extrinsic. So intrinsic means pure semiconductor, means there is no doping, no impurity has been added to such semiconductor. That's why we call it as pure or intrinsic semiconductor. And the conductivity of this intrinsic semiconductor is entirely due to the presence of intrinsic charge carriers, that is electrons and holes, and it's not because of the impurity or the foreign atoms present in that lattice. So the reason for conductivity of intrinsic semiconductor is due to the presence of intrinsic charge carriers only, and these intrinsic charge carriers are of two types, that is electrons and holes present in there in the structure, and no role of any impurity atom is there in case of intrinsic semiconductor. Now if we consider the crystal of a semiconductor, let it be an elemental semiconductor, for example it can be a germanium crystal or silicon crystal. So that kind of crystal, each atom has 4 valence electron and it share those electrons with the 4 nearest neighboring atoms to form 4 covalent bond. So this can be shown here in this structure. I have taken the example of silicon here, we can also take germanium. So both silicon and germanium have 4 valence electrons and they form covalent bond to the nearest 4 atoms in the way it is shown in the diagram. So now if there is a crystal like this, and because of the room temperature, as the temperature increases or because of the room temperature, some thermal energy is provided to those electrons, or we can say that thermal energy of valence electron increases because of the rise in temperature. Then in such case the electrons may break away from the covalent bond. So the covalent bonds here, such bonds break because of the increase in temperature. So in that case, one of the two electrons, if the bond break, one of the two electron leave the lattice and it leave behind a vacancy in the covalent bond. So whenever the bond break like this, here we have shown the breaking of bond. So suppose this covalent bond break, as this electron leave the lattice, the reason or the process of setting free an electron from a covalent bond and creation of this hole is because of the thermal energy which act as the ionization energy, Eg, which we have studied as band gap in band theory. So when the electron get this that much amount of energy, Eg, or we call it as ionization energy, it moves from valence band to conduction band, or we can say that it leave the lattice and the vacancy it create at its place, at its site, is termed as hole. So the vacancy of an electron with an effective positive electronic charge. So since electron is removed from here, so we consider it as effectively positive. So this vacancy which has effective positive electronic charge is called hole, and it behaves as an apparent free particle having charge equal to plus E. Since an electron is removed from that place which is of charge minus E, that's why we consider it as a hole of charge plus E, which act as apparent free particle. Apparent free particle in the structure. So the point that we need to note is, as we increase the temperature, it implies thermal energy increases, and as thermal energy increases, these free electrons get sufficient energy or sufficient ionization energy. That's why there will be a breaking of covalent bond and we get free electron plus hole pair, one pair for one covalent bond breaking. If one covalent bond break, it gave us one free electron and one hole, that means free electron hole pair we obtain, where hole is the vacancy created by the electron that move from that site and it act as effectively positive electronic charge, and the energy that is needed for this process is equal to the ionization energy, that is Eg. Now the number of electrons which set free at some absolute temperature T is given by the relation Ne is equal to C e to the power minus Eg upon 2 kT. Okay, so this is the value of electrons that get free from the structure at the energy Eg and temperature T. Here T is the absolute temperature at which we are observing the structure and K is the Boltzmann constant. Since one electron break and give us one free electron, one bond break and give us one free electron and one hole, that means the number of electrons that we are getting is equal to the number of bonds breaking, and it is also equal to the number of holes we are getting. So for each free electron it create one hole, from where it leave it create one vacancy there. So for each electron we have one hole in intrinsic semiconductor, which means the number density of free electron is equal to the number density of holes, as well as it is equal to the intrinsic charge carrier concentration. So for intrinsic semiconductors in which there is no impurity, in such semiconductor number of electrons or number density of free electrons is equal to the number density of holes, and it is also equal to the concentration of intrinsic charge carriers. So Ne is the number density, it is number density of electrons, NH is the number density of holes, and Ni is the intrinsic charge carrier concentration. Now there is one more point to note. Whenever such a structure is under the action of an applied electric field, then the holes present in the structure move in the direction of the electric field because of the jumping. Means these electrons here they will jump and change the site. Okay, the electron like this come here and the vacancy come here. If this electron move at this location, then the location of hole will change to this point. This is the site 2, which we get as the new hole location. So because of the application of electric field, holes can move in the direction of electric field, so they act as positive charge carrier, and because of that we get some hole current and we represent it by IH. So IH is the hole current, which is because of the motion of these positive charge carriers holes. Similarly, there are thermally generated free electrons which also give rise to an independent electron current. Because of these free electrons, thermally generated free electrons, we also get independent electronic current and we call it as electron current IE. So the total current in such intrinsic semiconductors is the sum of both the currents. That means total current is equal to the sum of hole current and electron current, that is IE plus IH. So that's how we can explain the valence band model for intrinsic semiconductor. In next video we will be discussing about the valence band model of extrinsic semiconductor. So for that, stay tuned and keep studying. Thank you.